Hi, everyone, and thank you for joining for today's session of the EDT seminar series. Today will actually be our last session for the current series, which we will continue with the 11th edition of the series in most likely in October this year, with the speakers and topics still to be announced. If you want to stay updated, feel free to check out our website on EDT.Community. You can also subscribe to our mailing list where we frequently, or when there's something to announce, we will send out a notification about upcoming talks. Also, if you are a researcher, a PhD student, or a practitioner of some sort, or know someone in this regard, then feel free to reach out to us so we can maybe schedule also a talk. You can find our contact information also on our website, EDT.Community. But now for today, our guest speaker of today is Giovanni Lugaresi, who is an assistant professor at the KU Leuven. Hopefully I pronounced that right and not totally off. And his talk, or what he's researching on, is related to digital twins, process mining, and Industry 4.0. And also today's talk will be related to digital twins and process mining. I'm particularly looking forward to this because, this is an everlasting topic, of course. How do we deal with the data? How do we effectively work with the data that emerges in a digital twin system? And having read some of Van Alst's work, I'm also looking forward to learn how the techniques in process mining can be connected to digital twin systems. And with that said, I would ask you, Giovanni, to take over and share your slides again, and would say then the floor is yours.
Thank you. Okay, thank you, Martin. So I hope you hear me well, and in case, let me know. So welcome, everyone. By the way, do you see my screen?
Yes, looks
okay. So welcome, everyone. So thank you for coming today. So I'm Giovanni Lugaresi. I'm from the Department of Mechanical Engineering in KU Leuven. I'm assistant professor, and I'm also PI in Plandersmeek Strategic Research Center in Belgium. In today's talk, I will talk about recent research topics in the research group. So as Martin was saying, how to integrate process mining and digital twins. So I will present a collection of recent works and also give you a little bit of a perspective on the current topics, current activities of the research group, so that it can also stimulate some thoughts of new research topics as well for you as well. So this is a bit of the outline of today's talk. So I'll give a bit of an introduction, of course, to understand the industrial landscape. Then I'll introduce a bit how this relates to digital twin, and the main topic, which is the internal services of digital twins, where process mining is related to model generation, so as a technique to generate models. I'll introduce a bit the techniques of model generation and model tuning, which we will see that is a technique to control the level of detail of the models. Then give a bit of a perspective on what is still left to be to do research on, and as I said, a few current projects. So with a few details on current projects that can stimulate some thoughts and some final remarks, of course. So just to give a bit of a perspective in general, this is the general industrial landscape of the last 2 to 3 years is characterized by what we could say complexity as a single word. We can, of course, we can find several reports so with different levels of details on the current state of industry, especially in Europe. But the general message is that Europe is under pressure because of different factors. So on the one hand, we have the obsolescence of some manufacturing systems together with their business models facing new challenges such as wage inflation, the difficulty to retrieve raw material, energy prices, and of course you can imagine also several recent news that are characterizing the last year. In general, therefore, so we are under European industry, especially, is under pressure, but we are also coming. So we are also living under the legacy of the last largest industrial revolution, which is Industry 4.0, which gives us still gives us a lot of opportunities to industry, especially the capability to process data with high frequency, to perform affordable data analytics, and to understand emerging behaviors in complex systems such as factories. If we look at recent reports, so I just take World Manufacturing Foundation as just an example, but you can find several others. So we have data that shows us that industry is investing more and more on digitization. And we are there are expectations that the investments in digitizations are just at the beginning, so they are just going to rise more and more in the next 3 to 4 years. One of the most cited technologies in this characterized by these investments is definitely digital twins, which is the topic of this group. So engineering digital twins. Of course, so there are again data that demonstrate that companies are investing in this technology, and we can find references on digital twins for not only for manufacturing systems, but also for building environments, and also for even a twinning of people, for example, also for example for healthcare. So definitely a growing technology. So we are focusing on, in this talk, I focus mostly, so when I say digital twin, is referring to the scope of manufacturing systems. So we are analyzing the digital models of manufacturing systems, such as a production line, a job shop, or a flexible manufacturing system. In the last, so we can also relate digital twins. We can connect digital twins as an evolution of the ways that digital models are being used in industry. So in the last, let's say 40 to 50 years, so starting from offline models used mostly for layout, or design decisions, such as assembly line balancing, for example, or generally for offline analysis. Then to what is generally called digital shadows, such as models connected to a physical system that is collecting data, and the data used to update the digital model, which then allows for analyzing different scenarios or performing ad hoc predictions. To then digital twins, which are characterized, one of the most cited characteristic is to have a bidirectional flow of information. which allows for optimization based on current conditions of a system, production control, and therefore also coordination. So managing, for example, maintenance plan in real time. In the last works and research, we have identified several research challenges that are preventing us from passing from digital shadows to digital twins for manufacturing systems. And today I'm going to dive deeper on some of these challenges. So in this view, I start to introduce the general claim of this talk. So when we are basically claiming that the reliability of a digital twin, or if we want the capability of a digital twin to be supported along its life cycle, or if we want to say informally, to remain alive during the operation of a real system, is dependent on the harmony between what we call internal and external services. I will explain a little bit what we mean by that. So in this view, we have on the lower side a manufacturing system, which can also be of different types, so assembly lines, job shops, and again, you can think of your favorite ones. And these systems are we are modeling this system, and therefore we have a digital model. And in this orange box, we can collect different digital models of this system. When I say digital model in this talk, I mostly have in mind discrete event simulation models, but of course, we could also have an analytical model or even a data model, and others, of course. And this digital model is used to perform some services, something that the users of the manufacturing system need. For example, planning or predicting the performance of the system based on some inputs, or even more online decision-making, such as rescheduling or rebalancing a production line. This is possible along the life cycle of a system if we have also what is called the internal services, which basically are techniques and methods that support the existence and the update of the digital twin. So, for example, model generation, so being able to generate the model starting from data, so data-driven modeling. The ability to synchronize the system, the digital model with the conditions of the real system, recognizing a condition with a trigger. So, for example, identifying a condition that triggers the need of a decision, so such as rescheduling, for example, a failure that triggers a rescheduling decision. And then, of course, validation. So the idea to continuously verify if our digital model is correctly representing the performance of the real system. And then, of course, once if we need to update the model, then we could also need to modify our models and update the model. We have talked about internal services also in other works, and I would also refer to a previous EDT talk, actually. So we have identified several internal services, and today I will focus mostly on model creation or model generation. So if we look at model generation, so if we look at the literature, we can identify several methods to generate models starting from data. We could definitely identify process mining as the most popular technique to do so. And process mining is a technique that is concerned with the discovering and delivering insights starting from execution logs, so from data from a system. And the most popular techniques in process mining have been developed to model and enhance and improve business processes. So in previous works, we have identified limitations that were preventing the development of data-driven modeling techniques, so I connected to process mining, to be applied to manufacturing systems. So, for example, the capability to correctly identify the finite capacity resources, the capability to choose the level of detail, and the connection between the discovery model and the discovered model and the performance, so the validation of that same model. That's why we have been active in this field of research and in the last years, and I will give you some examples in this talk. Of course, we are also, it's fair to say we are not the only ones active, and you can find recent literature reviews that focus specifically on process mining in the manufacturing domain. What are those reviews telling us? So they are telling us in which type of processes recent works have focused on. Basically telling us that the most popular ones are production lines and manual or assembly processes. And then also which type of algorithms have been developed mostly. So I won't dive in detail on the different algorithms of process mining, but basically what this is telling us is that most techniques have focused on process discovery. So on the ability to discover the main characteristics of a system, and so the layout, the resources, and the dynamic of the system. And we have less works focusing, for example, on performance analysis or predictive process mining. We also have a few indications of which are the most common representations, so the formalisms that are being used to model the manufacturing systems. We are actually using also some of these most popular formalisms, so which I will mention in a moment. This in a recent work, I also tried to identify how this recent corpus of literature can be also related to a digital twin framework. So again, not diving too much into detail, but basically I tried to map where the main recent works have been focusing on if we look at them from a perspective of a digital twin. So again, taking a conceptual framework of a digital twin, trying to look at where most works have been focusing on, and we can identify works, for example, focusing on identifying event log preparation techniques, so preparing data to be used for a model generation or a model or a discovery technique. Some works on model update and validation, and definitely a few works on frameworks and on the services to manufacturing systems, so developing techniques that then perform a service useful for the users. Okay, now I will step back for a moment and give a general view on what are we focusing on when we say model generation, so or discovery in the last in these works. So I try to focus on I try to oversimplify a little bit, if you allow for it, just to understand. So we take a general manufacturing system. So the simplest one we could have, just two stations with material flowing between these two stations. And we assume that it's possible to track the material flow, so which is a reasonable assumption. Nowadays, you can find even the smallest components in manufacturing systems products they are tracked. They are typically tracked. And even in manual processes, we have often the need to, for example, scan QR or barcodes by operators. So assuming to have data of material flow is a reasonable assumption. Starting from the material flow, we can collect them in event logs, which are basically giving us, of course, a lot of can be a lot of information, but the general the most important columns that we look for a timestamp, of course. Then an identifier of the part or the component that we want to track, and then the activity or the location in the plant where this activity has taken place. Starting from the event log, we can then identify, so looking at each part one by one, we can identify what is typically called a trace. So the history or the sequence of activities that a part has been doing. And we can do that, of course, for each single part. Starting from this, we can then use this information of the traces. So, for example, part 1 went before from station 1 to station 2, of course, in this oversimplified example, and then generate what is called graph models. So, where each we have a directed graph here, for example, where we have in each node represents an activity. And an arc represents the precedence, so the activity 1 came before activity 2. Of course, this is not enough because we are not keeping track of characteristics of the manufacturing system. And here I give you the intuition that was also the base of our recent work. So, for example, we know from the literature that if between two stations there is a queue or a buffer, we know that the capacity of this queue is essential to estimate the performance of the entire system. This is typically called the buffer allocation or the buffer level and so forth. We know that it's a very important characteristic of the system. And of course, it's definitely realistic. So in different systems, so you can find queues of any sort. So what we do is basically we can look back at the log and look at how many parts have been accumulating between station and use this inferred buffer capacity as a way to enrich our model. So if we go back to our simple graph model here, then, for example, the capacity of the buffer between the two stations can become a property of the arc. Okay. Why are we generating graph models? Because we know from the literature that then these graph models can be converted to discrete event simulation models, for example. Or other formalisms such as Petri nets as well. So this is why we are focusing on this first level discovery, because then we know that we can progress quickly to an executable model. Once we have discovered the model, then we also notice that we have a different challenge that is typically called the aggregation level or the model tuning problem, or well, in process mining you can find some reference of complex models that are called spaghetti models because they look a bit like spaghetti, of course. This is generally the problem is about choosing the right level of detail for the scope of our model. So if we think about the real life, this is something we also do. For example, when we choose the correct map, when we want to travel from point A to point B. So if we are in a city, we need to identify the different roads within the city. and use the proper map of the city. But if we need to travel from one city to another, keeping track of the roads within the city may be even irrelevant, right? So this is similar to what we want to do for a manufacturing system. So to give you a simple example, so for example, if we have a system such as this one, where we have this one on the top right, where we have a conveyor system that enters a robotic cell. Often it occurs that in robotic cells we have a recipe on what are the activities to be performed. And typically they are determined by the programmers, and therefore they might follow a specific pattern. And in some cases, we might not be so interested in following each single step within a robotic cell. So what we wish for our model is to simply aggregate the activities occurring in a robotic cell to simply perhaps in a single node and saying, okay, this is what occurs in the robotic cell. Okay, but then if we use model discovery, we will get all the nodes for each single task of the robotic cell. So with a model tuning technique, what we wish to do is to simply identify the pattern of the robotic cell. For example, events that are occurring with a deterministic time difference one another, or with a specific pattern, and simply then aggregate them in a single node. We can do that with the techniques that we developed. So, for example, identifying this property of having a pattern between different events, and then using this as a score to drive this simplification of the model, or the tuning of the model. So finding the best adjusted model to then decide which activities to cluster. And we have done this also in recent work in a real case where we looked at a log of 5,000 events, and then we generated the model and also identified very rapidly which activities belonged to the same stations, so to also drive the correct level of detail of the model. Of course, what I was talking about are only a few of the research topics that we can work on. Here I also identified others that are interesting. So for example, I talked about the inclusion of manufacturing system properties, such as buffer, and controlling the level of detail. But we can also think of others. So for example, in a manufacturing system, we typically don't have a single object. We have not only one part, but typically parts are assembled one another, or then they are packaged and delivered, for example. And keeping track of each single part type in the system, if it's related to one another, then it can become complex. And this is in the process mining literature typically called object-centric process mining. And there are recent works also in manufacturing. In other situations, we might be interested in keeping track of manual tasks, such as in a manual assembly workstations, where perhaps tasks are tracked by a video. And I will show a little bit on recent projects in a moment. Another thing that we might want to do is to keep track of policies. So, for example, how is a queue loaded and unloaded? So is it a first in, first out, or a last in, first out policy? We can also identify this from the data, so to correctly represent policies in our models. And we can, of course, think of other opportunities, for example, identifying rare events. So, for example, a rework. If we generate a graph model, we might weight in the same way each node but actually maybe some nodes have a different importance than others, and therefore we might want to keep track of it. And then, of course, to keep track of the importance of some nodes, for example, some parts of the system might be, such as bottlenecks, for example, might be the ones that determine the system performance. So perhaps the 80% of the performance of a system might be determined by 20% of the activities. And of course, we might be very interested in reflecting this in our digital models as well. So so we are also active in these topics. So I will just mention a few. So for example, for identifying the policies, we have a recent joint work with the Politecnico di Milano, where basically what we do is we generate a graph model that is, as I explained, for example, starting from a directed graph and then converted to a discrete event simulation model. And then we enrich this model not only with the system properties, but also keeping track on the state. So for example, identifying the buffer levels across along a time horizon. And since a policy is basically a function that connects a state to another, if we can keep track on the states, then we can also identify the policy that best fits the data for a certain time horizon. So then we try to identify production policies from data. And then, of course, represent them in the digital models. And we have preliminary results that show that this is working for simple systems. In other recent works, we are trying to keep track of the MES, so the manufacturing execution system. So, and this is basically related to the fact that some patterns in the data, they are actually not there randomly, but they are determined by a control action from the control of the system. So the MES is the information system that allows for it. And what we do is basically we represent the control system, the control of the real system in the digital model. And then, of course, then we enrich from the digital model, not only with the system graph model, so the discovered material flow routing and layout and resources, but also with the control system from so the MES, so the execution system. In other recent projects, we are active in Leuven. So we are using model generation for a disassembly line. So where basically, again, we do generate a graph model, but we do not only generate the graph model of the system, but we keep track of the product conditions. So the idea is that in demanufacturing, it's important to keep track on which material is entering our system. Then in this project, we are also keeping track of the DPP, so the digital product passports, and we are enriching the knowledge of the system, but also of the product. So with each product that enters the system is potentially causing a control action on the system, such as, for example, deciding which disassemble station to use based on the conditions. And this is it's a recent project that we are developing, this prototypical framework that is currently being done in our department. In another project, we use model generation for keeping track on the current balancing solution in the system. What typically can occur in a system is that when operators are free to allocate some tasks from one station to another, then we might observe different balancing solutions. And then, of course, we use this to and try to decide online, so how to rebalance the line, so to send operators, send instructions on what would be the most proper way to balance the line based on the current conditions in a system. So we have done that in a simple project in collaboration with the Budapest University of Technology and Economics, and this work has also won the Best Paper Award at ACMS 2025. So I'll also refer to the paper if you are more interested. And this relates to what I was mentioning before about workstations that are controlled by a video, for example. So in this project, for example, we have assembly kits that are monitored by a video system, by a camera. So, for example, in the kit trays, we have a kit tray for each workstation. We have 3 workstations. Based on the camera, based on what happens in the camera, we can identify which parts were assembled, and then, of course, keep track, so log the assembly actions by the operators. And then the idea is to, again, send back instructions to the line. In this project, we have envisioned a system online that sends instructions based on, for example, which rebalancing solution would be ideal, for example, based on a prediction of the throughput for the rest for the rest of the day, for example. Okay, so I gave a few perspectives on recent projects, and I want to start to conclude with some final remarks on the research. I have I've mentioned some techniques, but we can also identify from the papers that so most techniques are being used on the discovery phases and on relatively simple systems. So definitely there is room for more research to identify how to manage more complex systems. So, for example, in a job shop, we have the routing is very complex between, we have a complex schema of routing between different workstations. And definitely this causes complex models, and we have to properly manage the level of details of those models. We have definitely room for unstructured data, for example, on video-based discovery. And then, of course, I didn't mention much, but so now I assume that we have already chosen the formalism. But in some cases, we might want to use different formalisms based on which which characteristic of the system we want to discover the best. Not all the formalisms are best to do the same, all the jobs. So we might want to use joint mining approaches, so where we use different formalisms, for example, to identify the relationship between different system states and the material flows. And then, of course, we might want to work more on model tuning methods. So, for example, integrating AI methods such as graph neural networks that are promising techniques that can be connected to a graph model. And so, as I mentioned, our research group is active on these topics, but not only these topics. So I mentioned mostly model generation techniques, but we are also active on, for example, doing the discovery to identify the behavior of an operator. So, for example, an operator that learns which are the best techniques to assemble or disassemble a product. So this is actually also a model, and the model must be updated online as the operator is learning, for example. So this is also basically a discovery that is done online. And I mentioned a bit about the demanufacturing, and the fact that we are active, for example, production planning and control for demanufacturing. Then we try to build lab scale models for the demonstration. So once we develop a digital twin, we want to test and we want to demonstrate that a framework is working, a framework and an architecture is working, and of course developing digital twin conceptual and software frameworks. And if you want to follow up with our activities, so we are recently being involved in EuroFMX. This is a Horizon Europe project, and is one of the largest AI Horizon Europe projects. So the budget is 46 million, such a very big project. And in this project, we will be active on generative AI techniques for manufacturing, which gives us, of course, the opportunity to extend even more the techniques that I mentioned, of course, taking into account the recent developments on generative AI. We are active in also in the Winter Simulation Conference. I mention it because we have written tutorials, which are papers that I would suggest in case you are interested in these topics. I think they can summarize well the research that I mentioned. And we will have also new tutorials in the next conference, which will be in December. So with this, I think I should be on time. And I thank you for your attention. And if you have any question, I'm very happy to answer.